So in this topic, we will discuss what happened with shear joints that statically determinate. For this, I want you to watch a video, and again, the same that we watch, same company, Flexible Assembly Systems. You can take a look at them in on YouTube.
Shear strength is an important mechanical characteristic of a threaded fastener. It is a fastener's ability to withstand loads applied at a right angle to their bolt axis. A single shear will cut a fastener in half along one transverse plane. A double shear cuts the fasteners into three pieces along two transverse planes. The ASTM and the ISO have different standards for measuring shear strength. We will use a generic formula and approximate material values for this demonstration. Here's our fastener. It is made of low-carbon steel and has an ultimate tensile strength of 440 megapascals and a tensile yield strength of 370 megapascals. We can use these formulas to approximate what our ultimate shear strength and our shear yield strength are. Next, we will put our fastener into a double shear pin joint and mark where the two shear planes are. The shear force, or the load at each end, is 500 newtons. Since there are two shear planes, the load is distributed between them. Each shear plane experiences a shear force of 250 newtons. Next, we will calculate the area of the shear planes. Since the bolt is a cylinder, the shear planes will be circles. We could use the formula pi divided by 4 times the diameter squared, which gives us an area of 78.54 millimeters squared. Next, we can calculate the shear stress at each plane by dividing the shear force by the shear area. In this example, the shear stress is 3.183 megapascals. Our fastener's shear yield strength is over 65 times the shear stress it will experience from a load of 500 newtons. These photos from a NASA study display two more variables. The threads of a fastener have a smaller shear plane area and will break under weaker loads, and that the changing of the shear angle to less than 90 degrees creates a larger shear area and increases the load that the fasteners broke at. All this proves how important it is to understand the forces which your fasteners will have to withstand during their use.
Okay, so that kind of gives you an overview of the purpose and how these shear bolts really work. So they got three cases. Let's suppose this is one case in where there's no preload at all. So there's no loads in this. So if I'm going to find, if you want to find what is the load here, this load is equal to 0. There's no loads in here, okay? There's no preload. So if I apply this, in that case, and I do a free body, you can see this is my shear force, and this is my bearing stress. That is the contact stress between my bolt and my member. Now, most of the cases, we don't have these cases. What we always do is we do preloaded bolts. So in other words, you do have axial loads in this direction. And this is creating a pressure load here. And then mainly what you have is friction. You don't, in such a case, your members are not necessarily adding an extra pressure, applying pressure to the bolt itself. So it's mainly a strength of what the members can handle and if your bolt can handle the stress here. But it will never, it's rarely going to feel like it's going to fail in shear. Okay, it can if it exceeds exceeds the friction value that I apply between the surfaces, mating surfaces. Now in this case, it's a tension bolt like the one that we discussed in the previous topic. And in this particular problem, you see that all the loads are basically in tension. So to understand a few things here, and if it's a single shear, and I apply a load there and apply a load there, and I do a free body diagram, my free body diagram action reaction is going to look something like this. And if I cut through this plane, then I'm going to have a force that's equal and opposite in this direction. If it's a double shear now, and I take only this guy, then you can show that the total F is going to equal to P and P. Okay. So in this particular case, what you will have is the P is equal to F. Here P will be equal to F over 2 because this system has to be in balance, right? If you got F here, you can have F and F here, then this is not in equilibrium. So this is the total load acting in each member. This is the load acting at the joint, okay? Um, and so the couple of things that I want to point out here, if they are not preloaded, this is how you will find your P. When they are preloaded, you have to consider your friction between the mating surfaces and the tension of your surface. Okay, so this equation is also important depending on the case that you're working on, especially if the force is clamped. Um, so you have most of the time when you have a case of multiple fasteners. This is one example. And you can see this is how you will outline your, as an engineer, this is how you will outline this for your the manufacturing team. You can see that this says these are pre-bolted. And this is an I-beam, if you would. So what you have is you got two surfaces. You have one surface, you have an I-beam, and then this I-beam comes here. You have an I-beam. Then what we wanted to do was we wanted to attach another I-beam, maybe because of repair. So you repaired one part and you don't want to redo the whole thing again. It's too costly. So in such a case, this is a second I-beam, if you would. In such a case, what we do is we will go ahead and we will attach this with fasteners here, okay? And then top here, we will also take it with another surface here. We put another plate here on the top, and we'll add fasteners to this, okay? These are in tension. These are meant to be working shear. Actually, both of them work in shear. And this is saying these are actually preloaded. These are preloaded. And so you can see this is how this really works. Now, there are two ways I'm going to find the fasteners, and this is important that you pay attention. One is a PS. PS will be row fasteners. So rows go in this direction, right? Especially if I'm working in something that will be affecting only in this direction. Then I have one, I have two, I have three, and I have four. So I would say F divided by 4, that would be PS, okay, in this particular example. Now, another case, pay attention, this is PTS, okay? So the total load here is for the type of application, and we will talk about that when I'm going to use one and when I will use the other. Here, I need to use all of the fasteners that I applied here. So there will be 1, 2, 3, 4, 5. I have 3 and 4, so it's 16. I will divide this by 15. I'm doing this only on the web. I'm not considering the fasteners that are on my flanges. Okay, so this will be your PST for this particular example. Okay, so if I keep moving on, you have to know that we have to keep a standard value 1.15. And if you want any additional factors we have been doing, then you will have 1.15 and then you multiply that by any additional factors that you have. Okay, so let me discuss the typical modes of failure. Typical modes of failure, bearing failure. In this particular case, it means that your fasteners penetrated inside the member, the plate. So that's called a bearing failure. That means your plate was not strong enough. When you do this analysis, you have to analyze both the bolt and the member. Okay, we have to make sure that both are equally strong. So this is a bearing failure, and we have to make sure the bearing has enough bearing capability. This is what we call splitting failure, because basically it starts on this edge, right? And it keeps peeling off, but it peels up in this direction only. This is a shear out. Basically, it doesn't have the capability, so this basically pulls all the way out and comes out. Okay, so the failure happens like this. Okay, it just keeps moving in this direction. So if I keep moving, this will keep moving in this direction. So that's how the failure occurs. Here, this is a block failure where when you pull this whole thing comes apart as a block. The other one that's very typical, and especially aerospace structures, we care a lot about that. That's net section failure. Net section calculation is this one that basically when I apply this tension, it tears up here. Okay. Um, so with that said, let's see how we evaluate these members. Remember, this is PS. PS was in the number of rows. Okay, fasteners in rows. So in this case will be 1 and 2. Okay, so if I had a 3/3, not 2 in this direction because the failure is occurring in this one, the 1, 2, it would be 3. Okay, then there will be 3. Um, and then in this particular case, I'm using yield tensile. A and the value of AB is T times T. So this is the it will be the thickness. Uh, it will be this distance over here, and this is the diameter. So that is the value I will be using there. So it's the cross section value that we are really careful. We are interested in. Okay, this cross section, this value right there. Okay, thickness over the diameter. So I have the diameter, this is D, and the thickness that goes inside the plane. Okay, and that would give me a factor of safety for this, and that has to be bigger than 1. Has to be bigger than 1 because remember I only included 1.15 here. Okay, so next section calculation. So basically the next section consists, I'm going to do this. I'm going to only consider this section where I have contact. I have to remove what happens in the cutouts. So you have W minus diameter 1, diameter 2, you have 3, then you go 3, etc., etc. And it's perpendicular to the load, okay? And I'm going to use PS in this case, okay? PS will be in this direction, okay? Will be rows, that this is affecting the rows here. And the next section will be divided by sigma n. Okay, let me go back here. Just want to clarify. I think when I say PS, if this is bearing failure, this has to be in row, perpendicular to the load. So it has to be 2. If that was 3 rows, it's 2. Okay, you always go in perpendicular. So if this is rows, these are columns. Okay, just want to clarify that. And this is the equation. Once you find your next section area, then you calculate this, and you want to make sure that this is also satisfied. Another mode of failure is the edge shearing. So basically, this is talking about this shearing. Here in this particular case, I use all the fasteners. So PST is actually divided by the total fasteners or bolts. Okay, this is a shear. So you can see I will use SYS. This is SYS because it's shear. And then, so this SYS equal to tau. Tau is equal to this. Your area S is this area because shearing. Okay, so it's this cross-section area here. So it will be T and then A. It will be this distance A right here. Okay, E is the center from this, and you subtract A. Another way to write this in the manufacturing process, you always want to keep E over D distance bigger than 2. So that's to ensure that this does not occur. And if that's the case, then your equation actually looks something like this. Okay, this is a more common equation that we use. And if nothing is given, just take gamma equal to 2, and you should be good enough. You should be ready to go. Okay, unless sometimes you take as high as 4 or 2 or maybe 3. So it's all going to depend on your problem. Okay, so you have to go from one case and another. Then you have bearing failure. Now this is the failure of the bolt. Okay, these were failures of the members. So we are talking about these members. Now you have bearing. So bearing stresses apply to the load. and this is PS. Remember, this is number of fasteners per row. Uh, that's what this PS really means. And then this is same as T diameter times the thickness. Um, the failure of the bolt, I want you to pay very close attention. This is not trivial. It goes out of the norm and how we typically do these problems. First of all, shear. This is what you will use is a total. This is PST. Don't just you have to be very careful with this. And then if you want to find your proof shear strength, take the proof shear strength divided by 3. And the shear area is pi to the squared divided by 4. And then if no thread is extended to the members, this is what we always want as whenever we can ensure this. So this is the threaded area. This is your bolt. So what you want to do is you want to keep your members always uh, outside the area of the threaded area. So you can have one joint, you can have something like this, and this is not threaded. However, if it does extend to the threaded for some reason, so what I mean is if this does go something like this, in that case, you want to use only the portion, this portion has to be also evaluated, and then use AR of the root, and this comes from your tables A1, A1, and A2 portion of the bolt. This is the only thing that will be different between this and this. Okay. For the axial stress, you want to make sure AT comes from this table as usual. This is just like the previous example that we did for tensile loading. You want to make sure that this load is less than SP. Then the last case is bending. Bending is given by this equation, and the bending in your fastener is given by ND times B. This is your design factor. Don't forget that, and this has to be less than SP. Okay, but what do we do with factor safety? So this is where I need you to pay attention. In factor safety, what we do is we calculate the stress ratios. So you basically divide each one of these cases by the proper. So for the axial case, I will divide by SP, proof strength, and R and moment I divide by proof strength. But shear I will divide by shear proof strength. And then if 1 over R, 1 over RA, 1 over RB, and 1 over RS all have to be bigger or equal than 1. Also, but that's not what I care for so much. This has to be met. But then based on Mises criterion, you can show that your factor safety of the bolt is actually given by these ratios. This is what we typically and commonly do in aerospace industry and many other places. This has come from old NACA tech notes. There are another variations that you got many different variations for this, many different interaction equations. This could be another such equation. Um, I will not tell you what we do in our industry, but there are also not old NASA tech notes that actually talk about this. Brune has a very good um, topics on how we handle this kind of things, but we have to do the stress ratios. Okay, this is very different from what we did for uh, power screws. Okay, in this particular case, you have to do interaction equations. You cannot use just the von Mises equation like you always did. Okay, so with that said, this is kind of how we will do the analysis. And next we will just do an example to see how all this is applied.